Graphene is the ultimate foil with the thickness of an atomic layer. 2 sheets of graphene is therefore the ultimate book. We have shown that it is possible to read each one of the pages of this book separately using a laser light, and even more during printing. What is written, the electric charge or the internal deformation of the sheet, is certainly less bewitching than its verses, but is of great technological interest. Indeed, these 2 parameters make it possible to adjust the physico-chemical properties of graphene for applications in fields such as electronics or sensor development. We have shown that these parameters can be controlled, written, and read separately on each graphene sheet by subjecting it to high pressures. We did this by using different carbon isotopes for each of the graphene sheets and taking advantage of their interaction with a laser beam using Raman spectroscopy. The results presented here have been published in 2020 in an article entitled Strain and Piezo Doping Mismatch Between Graphene Layers. We are going to introduce the main results of the work. More details can be found in the paper. The sample was submitted to high pressure using a diamond anvil cell. This setup allows to compress a system composed of the bilayer graphene sample made of 2 isotopes and supported on a silicon dioxide substrate in a cavity between 2 diamonds. The substrate and bilayer graphene system is immersed in a fluid, the pressure transmitting medium. A ruby chip allows to calibrate the internal pressure using its luminescence. We focused a laser beam to probe the graphene phonons using Raman spectroscopy. Under high pressure, the pressure transmitting medium will densify and eventually become solid. The silicon substrate shows a compressibility much higher than the graphene carbon-carbon bonds, and then, through the effect of pressure, will create a biaxial compression as it has been shown in the work of Bousige et al. Due to the different mass of the carbon atoms in the 2 layers, the Raman signal shows 2 components. Here we show the G-band Raman signal evolution with pressure of the supported graphene layers under high pressure using nitrogen as pressure transmitting medium. The G-band hardens with pressure due to the biaxial compression and the pressure transmitting medium densification. The carbon-12 bottom layer in contact with the substrate has a different environment than the carbon-13 top layer in contact with the pressure transmitting medium, and then the evolution of the difference of the G-band position, which we call chi, can provide information about a mismatch between the 2 layers. We have followed the evolution of the G-band for the bilayer system in 3 different pressure transmitting media: argon, nitrogen, and a mixture of methanol and ethanol alcohols. Here we show the evolution with pressure of the position of the G-band, its full width at half maximum, and the difference in position of the 2 peaks, chi. All this is discussed in detail in the manuscript, as well as the evolution of other Raman peaks as the 2D band. Here we will only discuss the evolution of the chi parameter with pressure. Argon and nitrogen are 2 inert media, and we only expect mechanical effects. We observe that the variation of chi is always positive and shows in particular important changes at the solidification or solid-solid transitions of the media, shown as vertical discontinuous lines. This can be evaluated as a strain difference between the 2 graphene layers, which is 0 when the pressure transmitting medium is a fluid, and becomes non-zero when the bilayer graphene system finds itself sandwiched between 2 media of different compressibilities. The differences in the mechanical solicitation slightly decouple the 2 graphene layers. In the alcohol experiment, chi evolves very differently, and that for the 3 experiments we have done. After realizing that in one of the experiments the system partially unbinds from the substrate during compression, we were able to evaluate that, in addition to the compressive effect, there was a charge transfer effect which is more important for the top graphene layer in contact with the alcohol medium than for the bottom layer. With the help of some theoretical results, we were able to evaluate the evolution of the doping difference between the two graphene layers. This piezo doping effect is originated from the alcohol interaction with the top layer. Reveal its detailed mechanism would need further work. We have then shown that for argon and nitrogen, a strain mismatch between the graphene layers develops with pressure. This can be used to better study the non-hydrostaticity of different pressure media. For alcohol, a polar medium, we have shown a piezo doping effect which opens a new path for piezo sensing or for strain engineering. The study of other polar media combined with modeling should allow to better understand the physico-chemical mechanism involved. Thanks for your attention. More information can be found in the manuscript and in other references from our group.